Let's do number 8. So we have a wire that is moved parallel to a field. What EMF is induced? So we already did one where we had to really visualize what was happening. That was more conceptual. This one has numbers. But even though it has numbers, you still want to conceptualize it first. So what's happening is this wire is moved parallel. So V is parallel to the field. This is B here. So when V is parallel to B, the charges in here do not experience a magnetic force. So that means that the charges will not separate in this rod or in this wire. So there's not going to be any EMF induced. So you really want to visualize it. Now, the way that there would have been an EMF induced, let's say for example that the bar was moving this way, but now that we had a field into the page, then now you would point your fingers to the right. You would fold your fingers into the page, and if you do that, your thumb will point upward. And that tells you that the positive charges in here experience a force upward, the negative charges will experience a force here. So for this case, there would be a potential difference. Now, once you know that there is a potential difference induced, an EMF induced at the ends of the wire, then all you have to do is plug the numbers into E equals BLV. But before you do that, make sure that the answer is not 0. Sometimes the answer is 0. For the next one here, so we have a coil that is rotating, and we're looking at what frequency we have to rotate it to get the maximum induced EMF. So what you should visualize whenever you have a coil that is rotating through so there's some rotation here, and there's some external field, then what you should visualize is this is what a generator is. That you're rotating this loop, the flux through it is changing, and that's going to induce a current in the loop. That's the principle behind a generator. So if you realize that, even though it doesn't say generator anywhere, then you can jump straight to the equation for the generator that tells us how much EMF is induced. E equals NBA omega sine of omega t. We want the maximum induced EMF. That means sine is 1, that's the maximum value, so we don't care about sine. And we need to solve for frequency. So when it says frequency and the units are in hertz, that means we're looking for F. But omega is the angular frequency, that's equal to 2 pi f. So we need to really solve for omega here. Omega is E over NBA. And we can say that omega, I'll go ahead and replace omega here with 2 pi f. And then solve for F. So F is going to be E over NBA divided by 2 pi. So that's how we're going to solve for the frequency. So let's see our givens here. The EMF, E is 8 volts here. The number of turns is 200, that's N. B is right here, 30 milliteslas. Milli is 10 to the negative 3. The area is 300 centimeters squared. So once again, make sure to convert that area to meters squared. So 300 centimeters squared, that's going to end up being 0.03 meters squared, because you're going to have that factor of 10 to the 4 like I showed in a previous example, because you have 100 squared centimeters squared equals 1 meter squared. You have to use this as your conversion factor. And that's all of our variables, so plug and chug into here, and you'll get a frequency of 7.1 hertz. If you solve for omega in this equation, instead of f, if you do solve for omega, you'll get 44.4 radians per second. But make sure that then you divide by 2 pi to get that frequency. Let's do the next one. The current in a coil with a self-inductance of 1.5 millihenry, so that's the inductance, 1.5 times 10 to the negative 3, increases from 0 to 1 amp, that's the change in the current, change in I, in a tenth of a second, so time is 0.1 seconds. What is the induced EMF? So this is understanding that one way that we define the induced EMF when we introduced inductance in the first place is that the induced EMF depends on how fast that the current is changing, because the induced EMF depends on how fast the flux is changing according to Faraday's law, and how fast the flux is changing, how fast the magnetic field is changing through a loop is going to depend on how fast the current through that loop is changing. So this was another definition that we came up to find the induced EMF, and we said that L, the inductance, was this constant of proportionality. So this does give us a definition, and we can plug in the numbers. We have the L, delta I, and T all defined right here. A delta I is 1. Plug those 3 numbers in and you're going to get 15 millivolts. Let's do a few more here. So this next one here says resonance occurs in an AC circuit when which of the following conditions is met. So we learned about resonance when we dealt with the RLC circuits, and the way that we came up with the equation for resonance frequency is we said that the inductive reactance equals the capacitive reactance. What we did is we ended up setting these two equal to each other. This 2 pi FL equals 1 over 2 pi F, and the C is over here in the denominator. And when you solve this equation for frequency, that frequency is the resonant frequency, and that's the condition for resonance when you have reached your resonant frequency. And we ended up with an equation for F, which we did F naught to really specify that this special case, when the two reactances are equal, gives you the resonant frequency. We got 1 over 2 pi square root of LC. But just in case you missed it, the reason that this condition gives you resonance when the two are equal is because we said that in an RLC circuit, we have an impedance. And I'm throwing a lot of things here out at you, but just kind of a refresher. We said that we have an impedance in the RLC circuit given by this quantity here. And we said think of the impedance of your circuit as the overall resistance of that RLC circuit. And when you want to have resonance, you want to have maximum current. And if you want maximum current, that means that you want your impedance to be at a minimum. You want to minimize this. Minimize the impedance, you'll get the maximum current. And finally, the only way to minimize this, the best way to minimize this, is to make all of this equal to 0. That gives you the smallest number possible in here. And that's why we're saying if we're setting this equal to 0, that means that the two reactances must be equal. That's how we got the resonant frequency.